Alright, so when you're going through your thermodynamics notes, I wanted to hit a couple highlights because, this is actually some pretty cool stuff. Thermodynamics is the study of work, heat, flow, and energy through a system and the movement of thermal energy. So, movement of heat. And you've been around, you experience this all the time. Basically, if you have something that's warmer, it's going to, touching something that's cooler, it's going to flow into it. It always goes from warm to cool. So in this case, if you open up the door in the wintertime and your parents say, hey, you're letting out all the heat, they're not wrong, because the heat wants to go from warm to cool. It always wants to settle to a cooler area. If you open up the door in the summertime and they say, hey, you're letting out the cold air, it's actually not true, because it always wants to go from warmer to cooler. So actually what you're doing is you're letting in the warm air. You're not letting out the cool air. Now if you say that to your parents, I do not take responsibility for any trouble you get in for being sassy to your parents, but I just thought that was pretty interesting. This is actually pretty important when we get into this, our calculations later on, because absolute zero is, 0 is 0 degrees Celsius, 100 is boiling and freezing. They made those numbers on purpose because they were awesome. But absolute zero is where all kinetic energy stops and molecules stop moving, and that's negative 273 degrees Celsius. You could also do it in Fahrenheit, but you just have to use a little conversion, which we'll have a formula for. Basically, what this says is there's 3 laws of thermodynamics. The zeroth law, which is funny because we don't say zero, zeroth, usually here first, is if 2 systems are touching, they're going to equalize each other, right? So if you have something that's warmer than cool and one that's colder, they're going to eventually equal out. That's why if you put an ice pack on your leg, it does cool down your leg. I do this every night. But eventually the ice pack and your leg become the same temperature. So your leg cools down, the ice pack warms up, they'll find a little happy medium after a while. And you got to put it in the freezer again. So these 2 guys touching equal out. This says if this guy's equal to that one and this guy's equal to that one, then they must be equal to each other. It's kind of like in math class. It's the transitive property. If A equals B and B equals C, then A equals C. So that's a zeroth law. The first law, energy can't be created or destroyed. The only way to increase thermal energy is by adding more with heat or performing work. Like, I know we have some bowlers out there. When you strike the pins, not only is a sound given off, but there's heat. And if you've ever pumped up a bicycle pump, if you pump super fast, you'll actually feel the tire heating up or this little cord heating up. Yeah, because you're putting in work. And this is the other one. This is what I was talking about with your parents. Energy always goes from hot to cold. So if you put your hand on a frozen pizza, you're actually giving your heat to the pizza. The pizza isn't giving its cold to you. You're kind of donating. And then if it's hot pizza and you go to pick it up, the pizza's giving its energy back to you. So it's like, you give a little, you get a little with pizza. Everyone loves pizza. And then, so the first law was, or zeroth law was that, kind of like transitive property from math. The first law was You can't create or destroy thermal energy just by adding work or more energy. The second law was it always wants to go from hot to cold. And a system wants to go from order, or a system usually goes from order to disorder. Entropy is the measure of how evenly distributed heat is within a system. Okay, so you can go through here. There's different ways of transferring heat. You're always going to lose some of it. Convection, you felt convection currents. If you use a air fryer, it's called a convection oven because it likes to move it around. If you've been in the ocean and you feel those little warm pockets going up and the cold goes down, a lava lamp is an example of convection current or convection. Where it heats up the bubble on the bottom, it goes up. Conduction is where you actually touch heat to something. Here is when we get into the crazy stuff with our equations. You have to get used to these symbols. So Q is transfer of energy in joules, M is mass, CP is specific heat capacity. Some things are better at holding on to heat. So if I had like a cast iron pan, the reason people cook with cast iron is not because they love heavy pans. It's because cast iron can hang on to heat really well. So if you put a cold steak into a cast iron pan, the cast iron is not going to like drop its temperature from 400 down to 100. If you put a cold steak in an aluminum pan, aluminum doesn't hold on to heat as well, and it's going to affect your temperature. You're going to lose that beautiful sear that you work so hard to get on your steak. And change in temperature. So there's our formulas. We have a few other formulas where the rate of energy in watts is your transfer over time. Your rate of energy of watts is conductivity times area times change in time over thickness. Basically, you're solving for this for different variables. These two are really the same equation. So we got a bunch of formulas to kind of make different calculations. Like if you dropped an 80 degrees Celsius, which is pretty warm because think 100 degrees is boiling, and you drop an 80 degree Celsius piece of aluminum into a cold water tank. Actually, that's not cold, that's room temperature. So you put a really hot metal block into a water tank and figure out how much energy was transferred if the water goes from 25 degrees to 30. It's obviously going to warm up. It's like putting, you got your sink filled up and then you put a metal pan in it after being on the stove, which I also don't recommend because you could crack some of them. Anyway, you can calculate how much energy was transferred if you knew the mass of the water, the specific heat capacity of water, which you can just look up on a table. There's a table for all these. How much the temperature changed, 5 degrees, and the heat capacity of aluminum, which once again you just look up. And then how much did the temperature change in the aluminum? Now it didn't say here the temperature of the block was 30, but we know from before that if you have two different temperatures of things that are touching, they will eventually equal each other. So you can find out, oh, this went from 80 down to 30, so I lost 50 degrees. So if I want to do my transfer of energy, it's this crazy equation right here, and they're going to equal each other. So I can do it with water. 1 kilogram, its specific heat, its change in temperature. It gained 21,000 joules, which means the other guy lost that amount. If you're wondering why it's here, this is rounded. It's actually 20,900. So here, you can actually figure out how much the block weighed because you know the amount aluminum lost is the amount water gained. So you can set this answer from water equal to your answer for aluminum and solve for mass because you have heat capacity and you have change in temperature, and you can find out it's a 460 gram block of aluminum. So you can use these formulas. You're going to see there's some more examples. Just go through them. Get used to the symbols. Get used to the formulas. We're going to do some of the problems in class together and kind of hang on to that. Then there's this thing called U value, and it's an overall heat coefficient, which means it is how well a material can conduct heat. So like I was saying, metals are going to have a much better U value. If you had an insulator, it would have a very low U value. So if U is how well something can conduct heat, R value is the opposite of it. It's how much you can resist heat. See how they're inverses of each other? So if you have a high U, you'll have a low R. If you have a low U, you'll have a high R. So basically, when you build houses and stuff, you want great insulation. You can tell how good an insulation is by looking at its R value. Next time you're at the hardware store, walk down the insulation aisle and check out, I bet anything they'll have R values listed on their insulations. So when you want to actually see how much heat your house is losing, bricks have certain R values. It's really low because bricks don't hang on to or resist heat change well, right? Air actually has a pretty good resistance to change. It's better, or actually, no, that's pretty low. Airspace, huh? Weird. And then, you know that foil that wraps your house, 7 R value. Fiberglass, this is your insulation, 19. That's what it's made to do. It resists heat moving. And then drywall has a little bit too. So if you want to know from the outside to your inside of your house how much heat is resisting, basically you add them all up. So you'd be like, oh, 0.56 plus 19 plus 7.2 plus this airspace of 0.17, and then the brick. So you have a 27.7 R value for your normal wall. However, some places there's studs of wood because it's what makes the frame of your house. This, you don't get to add the 19. Look, think about heat transferring. It would go through here. It would go through the air. It would go through the wrap on your house. Then it would transfer directly through a stud and then through the wall. Which is why if you have a heat gun, you know, one of those thermal temperature readers, I use it in my house. If you do it on a regular wall, you can actually tell where the studs are if it's an outside wall, because you'll get a lower temperature where the studs are. Or if you do it on your light switches on an outside wall, you'll find they're really cold because there's more air there and no insulation. Kind of cool stuff, and a good reason to get a thermometer gun. So then we got some other formulas here. Stefan's law. It's about how much heat is given off. And here you got your skin temperature, and when you walk outside in the cold, how much temperature do you lose, that sort of stuff. So it's just getting used to these different formulas. And then we have different applications, like you got your solar farms that get power. These are awesome. It's out in the desert. All these little things reflect the light in parabolas up to here. It would be blinding, but it harvests solar energy. And we're getting better and better at harvesting solar energy. There's geothermal, where you get the heat from the ground, from the earth, and stuff like that. So all of this is about thermodynamics, which is the change in temperature energy, change in thermal energy. So try this out, fill out your notes. Hopefully you have a general idea of what we're talking about, and then we'll get good at using those formulas. I'll do you have a formula, or you have problems to do with these formulas, and I'll do a couple of them in an example video. So look for that later in the week. All right, talk to you later. Adios.